In this video, we'll discuss the developments of analytic geometry, precalculus, and probability in the 15 and 1600s. Now, analytic geometry represents the use of algebraic symbolism to help us understand geometric concepts. And this took off during that time because symbolic algebra became more prominent during this time. Without that, we can't do analytic geometry. So think about the idea of ordered pairs being represented by x and y, writing equations of lines and equations of other types of larger degree polynomials instead of actually having to graph them. That's all versions of analytic geometry. We give most of our credit to the foundations of this from both René Descartes and Pierre de Fermat, as they both created what we think of as analytic geometry around the exact same time. Now let's look at those two men. René Descartes was both a philosopher and a mathematician. We often hear, I think, therefore I am, comes from Descartes and his philosophy. Now, he did a lot of works, one of which was in physics, but at the same time, he watched Galileo go under house arrest and be condemned by the church and end up passing away in house arrest. So he moved on from that work and instead created the discourse on method. Now, within that, he published 3 essays in the appendices, and one of those was on analytic geometry, and that's where his only pure mathematical work can be found. Within the geometry, the first part focused on the principles of analytic geometry, moving away from where the Greeks viewed variable both as the length of a segment, the product as the area of a rectangle, and the product of 3 variables being the volume of a rectangular prism. Whereas Descartes moved the idea of variable to that of a proportion. And by moving it to that of a proportion, we're able to look at the length being constructed for x for any power. Therefore, it's more easily able to be constructed. The second part focused on classifications of curves and other constructions of tangents to curves that are now obsolete. And then the third focused on the idea of how to determine the solutions to any degree polynomial equation. And that's where we get Descartes' rule of signs, which states that the number of positive, negative, and complex roots can be determined. Now, the way we do that is that we can look at the number of sign changes in p of x to determine the positive roots. We can look at the sign changes in p of negative x to determine the negative roots. And then what is left over then has to be all of the complex roots. We do have to pay attention, though. Once we get our maximum number of sign changes, the possibilities can also be a decreasing of 2 until we have either 0 or 1 possible solutions. So what I do is I make a table to represent all the possible solutions and root combinations once I've determined the number of positive and negative roots. So let's look at an example. Say we have 4x to the 5th minus 3x to the 4th minus 2x cubed plus 5x squared minus 6x minus 1. And we want to determine what are the possible roots for this polynomial equation. Let's start with the positive number of roots. So here I can say, yes, there's a sign change. No, there is not. Yes, there is. Yes, there is. And no, there is not, because we're going from positive to negatives. So here, the positive means that there's either 3 positive roots or 1 positive root, because that's 2 less. And it has to end in either 0 or 1. We can't have less than 1 or 0 roots. Now, what happens then when we plug in negative x? So f of negative x means we're going to plug in a negative x for everywhere in our equation. And then we're going to simplify that out so that our equation now becomes f of negative x equals negative 4x to the 5th minus 3x to the 4th plus 2x cubed plus 5x squared plus 6x minus 1. Now we look at those sign changes. No, yes, no, no, and yes. That means there could be a maximum of 2 or 0, because that's 2 less than where we started. So we have either 3 or 1 positive roots, 2 or 0 negative roots, and then the possibility of complex roots. So let's make the table. So let's look at what are the possibilities. What's the most that could be done? I could have 3 positive and 2 negative, which means there would be 0 complex because my index is a 5. Now I could also have 3 positive and 0 negative roots, which means there has to be 2 complex roots. Or I could have 1 positive and 2 negative, which means there have to be 2 complex roots, or 1 positive and 0 negative, which means there has to be 4 complex roots. Now, We have programs now in graphing calculators and other programs like Desmos that allow us to graph this instantaneously. But when we think about this is hundreds of years ago, they did not have those tools to help them graph instantaneously. So things like the rule of signs help them understand what were the possibilities when they have to actually graph this and how to understand it using the analytic geometry methods. Now, the other man, Pierre de Fermat, was actually a judge by occupation, but he loved his mathematics and considered a hobby for him to get away from doing that job. Because of all the things that he'd have to do as a jurist, he published very little because he didn't want to have to go through all that detail as well as have it always picked over and create controversies. So much of his work really was not published until his death 14 years later by his son. He does have an unpublished manuscript that went around much of Europe, and that is where we get his ideas of analytic geometry. But because it was formally unpublished and was only a manuscript, it didn't have the same influence as Descartes' work. Now, within his, he actually went about the idea of analytic geometry differently than Descartes. Whereas Descartes would start with the geometry to build complex equations, which allowed him to look at more advanced equations. Fermat started with the equation and used that to describe different types of curves and concepts in geometry. Additionally, in his appendix, he went through the equation of parabolas, hyperbolas, and spirals of Fermat. Now, beyond his work with analytic geometry, Fermat was also known to have worked on probability, doing the problem of points with Pascal. The difference between Pascal and Fermat's method was Fermat would go through and determine how many total cases there would be, where that would be 2 raised to the m plus n minus 1, where m represented the number of needed for person 1 to win, n would represent the times number of person 2 would have to win. And then he'd write the permutations that would go through the wins and losses, and that would create a ratio of how the wins and losses should be splitting the money. He was also considered the founder of modern-day number theory, with things like the Little theorem, where if p is prime and a is relatively prime to p, then a raised to the p minus 1 is divisible by p. As an example, say I have a prime number of 5. A is relatively prime to 5. So if I look at 8 raised to the 5 minus 1, I get 4,095. That is divisible by 5. His other major theorem that we hear about is his last theorem, which is there does not exist positive integers x, y, and z in n such that x to the n plus y to the n equals z to the n when n is greater than 2. Now, he never formally published any of his works and didn't often go through his theorems to prove them. In one place, it's asserted that he wrote this in the side of a book, and he said, I surely have found an admirable proof for this, but the margin's too narrow to contain it. And this is one of the things that was known about Fermat. Great genius, very strong understanding of mathematics, but did not prove much of his works, because again, he didn't want to publish, he didn't want to have to go through all those details. Eventually, hundreds of years later, 1995, Andrew Wiles goes through and proves Fermat's last theorem, and it takes over 100 pages to do so. Now, another famous mathematician and astronomer of the time is Christian Huygens, and his work is all over both mathematics and science. In science, he was able to help construct new types of lenses, both in how you grind and polish them, to be able to see better into the heavens. In 1655, he constructed a pendulum clock, and then years later constructed a book that explained how the clock works, both how to construct it as well as the mathematics behind it, as well as included in there was works on dynamics and various types of curves. After meeting Isaac Newton in 1690, he also wrote a treatise on wave theory of light, and was one of the first to explain how light travels in waves. Now, in that time frame, he also is doing work in mathematics. One such thing, after reading the works of Pascal and Fermat, he created On the Calculations in Game of Chance, which included 14 different propositions and 5 exercises for people to work out. Now, within those propositions comes one of the most foundational ones in probability, which is mathematical expectation, or the expected value. This represents the average expected winnings each time a game is played. So when we look at this, what he stated was that if P is the probability of winning, a sum of S, then the expected value is going to equal S times P. Whereas if there's multiple ways to win, and there's multiple sums that can be won based on those probabilities, then we can get the entire expected value by adding them together, so that expected values are additive. Now let's look at an example here. Say in a game, one will win $3 if a 6 is thrown and $1 if 1 or 2 is thrown on a single die, a 6-sided die. What's the expected value of the game? So we can use the mathematical expectations of Huygens with the sum here. And we know that the probability of a 6 times what I can win by rolling a 6 plus the probability of a 1 or 2 times what I can win on a 1 or 2 will be the expected value. Now I can't roll 3 different numbers. I only roll 1. So that's why this is looking at the average of what could be expected to be won over a long period of time. This is what will be expected each time I roll on average. So let's look at the different parts. So let's get that probability. So here I win $3 if a 6 is rolled. So the probability of rolling a 6 is 1/6. What I win then would be $3. But again, I can win more than that. I can also win if a 1 or 2 is rolled, and that would be $1. So a 1 or 2 represents 2 out of 6 ways of winning, and that would be $1 that can be won. Now I can multiply them, and that comes out to 50 cents and approximately 33 cents. Since we're dealing with money, we'd round it to the hundredth. I add them together, and that would be 83 cents. That means that the gambler, or one who's playing this game, would expect to win on average 83 cents. Now you can never win exactly 83 cents. That's why it's considered the expected value, because it's the average over the long time of playing this game.